Good evening. For this session on opportunities in research on materials, we have with us Dr.S.Kalaiselvam, sir. We'll now have a very short introduction of him. Professor S. Kalaiselvam received his BE Mechanical Engineering from Government College of Engineering, Salem. He received his ME Refrigeration and Air Conditioning from Anna University, India, and PhD in Mechanical Engineering from Anna University. He's been working as the head of the Department of Applied Science and Technology. During his tenure as head of the department, he successfully inducted a B.Tech program in Petroleum Engineering and Technology and M.Tech program in Industrial Safety and Hazards Management. Kindly accept our token of our love and appreciation, sir, a small book and a bouquet. Thank you, ma'am, Director Ma'am Umarani, madam. Thank you, sir. He's been in the top 2% scientists across the world according to the analysis compiled by researchers from Stanford University, USA. He received the Tamil Nadu Young Scientist Award by the Government of Tamil Nadu, Active Research Award by Center for Technology Development and Transfer from the former President of India, Honorable Dr. APJ Abdul Kalam, Best National Social Service Program Officer, Young Mechanical Engineer Award by Institute of Engineers, India, Young Scientist from the Department of Science and Technology, Government of India. He is also an active member in the Indian Institute of Chemical Engineers, Safety Engineers Association, and the Indian Society of Heating, Refrigerating, and Air Conditioning Engineers. Thank you, sir. Over to you, sir.
Good afternoon. Yeah, it's again a good occasion to meet the young researchers of Anna University. Today, my topic is opportunity in research on material. Basically, I'm a mechanical engineer. In mechanical engineer, I started my career in refrigeration and air conditioning. So there, we don't find any materials. So I really found very tough in publishing papers as well as the patent. So that is why I shifted myself to the material-oriented research. And whatever the stuff that you are seeing here, so that is the first one is a composite material, that is natural fiber composite material, and it's again our research. It's again a granted patent. And the second one, that is antimicrobial filter. So you all know that in case of air conditioning advertisement, so it's kill microbes, right? That's a way. Antimicrobial filters, it's one of our products. So it's again a granted patent. And nearby, it's a safety helmet. So normally people like me, we are very hesitant to wear helmet because whenever I wear helmet, there may be possibilities of hair fall, right? So obviously that is because of sweating. So to avoid that, we invented a cool and comfort climate. It's again a patented one. If you wear this particular helmet, you don't feel suffocation. You may feel very comfortable. And nearby, it's again a thermal jacket. It's again a patented. So here, normally very particular to the soldiers, so who are working in a very adverse climate. Example, let us assume that a soldier is working in a hilly Himalayan area. The temperature is very low, right? So in that particular situation, he may be very tough to work. It's our responsibility to make the soldier comfortable. For that, we invented a safety, that is thermal jackets. After wearing this jacket, he may be very comfortable to work for a minimum of 6 to 7 hours continuously. So here, this is my research profile. So here we have 3 granted patents, and 11 sponsored research projects, and 2 books our group has been published. And I'm contributed for 6 book chapters, and the total grant, it's around 3 crores. Why I'm projecting this, if I work on refrigeration related activities, I don't have this type of credential. If you try to concentrate on the materials, there are a lot of avenues in this. You take, let us example of engine, IC engine. I don't know how many of them are mechanical group. If you take an IC engine, even the long back that people are working with biodiesel and to alternate fuels, but still we are in use of diesel and petrol, right? If you take any conventional mechanical engineer or mechanical electrical or mechanical civil, if you work with conventional engineering perspective, it may be very tough to publish paper. That is a minimum requirement for research. At the same time, the innovation is also to be very limited. So these are all our research group. So far I have completed 12 PhD students, and the PDF students also I completed 2, and these are citations and publications. Yes. So this is a research book. So these are all some of the awards I received. It's again only possible because of doing research in materials. So here now we'll move on to this material. If you look at that, why we have to choose this material research? So normally, if you look at this material research, sometimes if you look at this, what's here? If anybody wants to work with the materials. So normally, you may find a new innovations, a new thing that you can find it. If you work with the conventional engineering or technology-oriented work, you don't find any innovations. That is what. And again, you have an opportunity to learn so many new things to work with the materials. Okay? And the salary, right? Normally, the salary is also to be very high if you work with materials. Okay, these are all the material engineering. If you can work with metals, alloys, ceramic, polymer, composites, semiconductors, or biomaterials. And these are all some of the porous material. If you look at this, the material perspectives. So here, if you look the material, it may be metals, or it may be wood, or plastics, or textiles. Even it can be applicable for the electronics industries. So this material, all this covers, right? And again, what I am going to do, because I know that it's a very heterogeneous group, so I don't want to go deep into any of the materials. Hence, with the mechanical background, if I go deep into mechanical perspective, sometimes it may get blurred. I will give only the overview, what we did in case of this materials. Okay? So these are all the various materials that you can work and you can find new innovations. Okay. So and again, my work is with reference to the nanotechnology. What I did as a mechanical engineer, initially, as I told that, I tried to work on this refrigeration, that is air conditioning. My research was to make the people comfort with reference to ASHRAE standards to meet all the indoor air quality standards. Initially, I worked for a period of 2 years. After working 2 years, it's really very tough for me to publish papers. And again, that particular work required a lot of, the funding is also required. Okay? So even though at the time I don't have any option, because you all know that as a researcher, you have to follow whatever your research supervisor says, right? So I used to work according to my research supervisor. Once I completed my PhD in air conditioning, I shifted myself to this material world. After entering into this, at the time of maybe in the 2006, I completed my PhD. So at the time, I have only two papers in international journal and 5 or 6 international conferences. So I found that if you work in the same field, it may be very tough to enter into this research world. So I shifted myself to the material world. So I chose the phase change materials, and the phase change material, whatever the stuff I'm at the first slide, it's all with phase change materials and the nano materials. So this again nano materials. So this overview of how the nano thinks. And again, my work is on this nano and energy storage. Okay? So this is again how the nano material, because as a mechanical engineer, I can't work immediately with other material. So I work for this materials on the energy storage. So you all know that why this the nano plays a vital role in case of any industry. Now, because if you use this nano, you can have increase in surface area. Anybody can say that if there is an increase in the surface area, you have a higher heat transfer or higher energy storage. Even in these days, the people are working on the hydrogen storage. Even for this hydrogen storage, this nanomaterials are very much helpful. And again, because of this interface and size effect, this nano plays a vital role. And again, as far as this nano is concerned, we will have this nano synthesis by two methods. One is top-down approach, and the other one is bottom-up approach. So as far as the top-down approach is concerned, you take, you all know that the paddy or rice, it's in the very macro size. If you grind it, what happens? It becomes a powder. It's in the micro size. Macro becomes micro. If you further grind it with the help of ball milling, other mechanical means, it again, the size reduces. That's a way they used to go with. This again a top-down approach. The larger size can be bring down to the lower scale. The other one is a bottom-up approach. Let us assume that if you want to make a cylinder, right? If you want to make a cylinder, what you can do? You can place 1 rupee coin, right? If you place 1 rupee, 100 1 rupee coins or 50 1 rupee coins in an inline direction, what happens? It becomes a cylinder. Similarly, what in case of this bottom approach, what we used to do, we used to build the size whatever you want by the atom level. The atom can be placed in such a way that, such a manner that it can be formulated whatever the size or whatever the shape that you want. And again, this particular one is a higher purity level. Normally, the initial people, if you want to work with this nanomaterials, they used to work for a top-down approach. It's one of the easiest method. And again, if you go for a top-down approach, even though it's the easiest method, there are a lot of impurities. I told that we are using some grinding or milling and other operations. So because of that, the impurities prevails in this approach will be very high. In case of this bottom-up approach, it's atom level you are supposed to work. And again, the impurities are, it's high pure level. So these are all some of the nanomaterials that prevails. It's one-dimensional, two-dimensional nano fibers, wires, rod, or a film, or even 3D nanomaterials. So here again, some of the nanomaterials. This is by top-down approach. How this is a nanomaterial, the center one is a nanomaterial. We can make this bulk material. You make it powder, and it can be converted into a nanoparticle, or otherwise the atom can be formed to be a cluster. That cluster can be made as a nanoparticles. And again, whenever I am going for this nano type of discussion, so I would have asked why this is more important, right? If you look at this is a property of carbon nanotubes. So normally if I ask a mechanical engineer which is to be the best conductor, which is the best conducting material? Copper. Obviously we all know that the copper will be the best conducting material. If you know that this carbon nanotubes is better than the copper. So in case of a carbon, if it's a bulk nature, what's the property of bulk carbon? Bulk carbon. It's an insulator, right? Bulk carbon, it's an insulator. If you bring down to a nanoscale, that insulating materials becomes a good conductor. This conducting property will be much more higher than this copper. And again, the transistor material, if I ask the transistor material, we obviously say that the better transistor material will be the silicon, right? So this particular carbon nanotubes will be the better than this transistor material, and it's again the heat conducting property. So because of this higher heat conducting property and the strength, the diamond will be the best. We used to say that, but this is twice the conducting properties, and the field emission is higher or efficient than molybdenum, and this is more thermal stability of this material is important. And again, in case of the aircraft applications, we used to say that the aluminum alloys, because of its a lightweight natures, because of the lightweight, we used to go for aluminum materials. So as far as this particular carbon nanotubes are concerned, this is half times denser than or lighter than this aluminum, and the strong, it's 25 times stronger than the steel. Even one of my research student, he worked for CSIR laboratory in that is Taramani campus. He worked on this civil engineering background. So normally what happens in case of a civil engineering background, you want to strengthen the structure of the columns and other beams. So in that case, in addition to that, he added this nanomaterials. So because of that, the strength increases. And he completed and he also published papers in reputed international journals. So here again, this the nanofibers. Sometimes what happens, the synthesis of carbon nanotubes may be very complicated, but maybe the initial period, instead of producing this or instead of synthesizing carbon nanotubes, you can easily, even in your lab scale, even without any specialized equipment, you can synthesize, you can produce this nanofibers. And again, this fibers, its diameter is less than 100 diameter, and it can be easily synthesized or it can be easily produced by polymerization and electrospinning. That I am going to tell how it has to be synthesized. And again, this properties, it's a high surface area like the carbon nanotubes. It's high porosity, and the diameter ranges from 100 to 50 to 100 nanometers. And again, this it's ultra thin. It's a very soft, and it can be easily mixed with the solvents. It's a soft touch, and whatever this particular one, it was produced in our laboratory. And this, the application of this particular polymer nanofibers, you can find that this nanofibers is used in case of tissue engineering, wound dressing, medical applications, sensor devices, electrical, optical applications, material. This nanofibers find wide applications. As maybe you may be an electrical engineer, or it may be electronics or civil or mechanical or any particular field, you can use this material. That is why I'm giving an overview. Okay, now because if you take electronics applications, you may look for an alternative for silicon. We have an alternative, and again the properties also to be superior. In case of a mechanical engineer, sometimes we look for a higher thermal conductivity or higher heat transfer coefficient. And again, this particular, if you use this particular nano material or nanofluids, you can find a high efficiency. Normally, in case of olden days, in case of automobiles, if it's stuck in between, what they used to open the bonnet and they fill water in the radiator, right? Do you ever notice that? But these days, anybody fill water into that radiator? You don't find that. And again, if you look at the previous, maybe olden days car radiator, the size is of very larger size. Is it right? If it's a larger size, what happens? Obviously, the cost will be higher. The material required is also to be very higher. So what these days the people are using, the fluid inside this heat exchanger or the radiator, it's a nanofluids. If you notice that if there is any leak in that particular radiator fluid, it's a color of blue or pink color, blue or sometimes it may be a greenish color. It's nothing but a nanofluids. Now because if you use that particular nanofluids, the heat transfer coefficient will be high. So because of that, you can reduce the size of the heat exchanger. If they reduce the size of the heat exchanger, obviously the cost becomes very reduced, right? Cost reduces. Similarly, in all the heat transfer applications, all the mechanical operations, we are trying to use this nanomaterials. Even in one of our research, we are putting an alternative for the plastics. So normally, if you all know that the plastics, and using the plastics, what we are suggesting, we use the natural fibers and we will make this composites. The structural and again strength-wise, it's similar to that of the plastics. Sometimes it's also equivalent to the aluminum composites. As I told that, how this can be, this nanofibers, it's an easy method. It's one of the simplest method of producing this nanofibers. Even in your house or in your residence or your laboratory, you can use this. It's a very simplest method. You can try this initially. You have a success, then you go with a commercial scale. If you look at that, this is only a syringe, right? If you look at that, this syringe with a mechanical arrangement, this is again a collector. What happened? This needle size, whatever the fiber that is coming out, it's again depending upon the size of the needle. So normally what happens, even if you apply any force, it will not come out. Because of this electrostatic force, it has to be come out. It's a very simplest method of producing this nanofibers. So these are all the properties. And again this, then the nanofiber production it's again depends upon this parameter, viscosity, conductivity, solution temperature. These are all the parameters that will affect the synthesis of this nanofibers. And these are all some of the nanofibers that was produced in our laboratory. And this is for some of them we used to use it for medical applications, and some of the nanofibers we used for supercapacitor applications. Okay, and this is for storage, battery storage, and these are all the materials we produced. And this is the gallium oxide nanofibers. It's again synthesis in our laboratory, that is for medical applications. It's again a PLG nanofibers. It can be used for medical applications. I'm a mechanical engineer, but if you know how to make this material, it can be suitably used for any applications. And this is again nanofibers. It was published in an applied surface science. So most of the one I don't have a time to quote it. And this is one of the method. This is for the fiber, the surface coating, right? Normally, in case of the surgical applications, you may find that it has to be coated with the copper material, because the copper will have higher antibacterial properties. That is why sometimes they used to say that you take food, you take some copper, it's antibacterial properties. So what we used to do, instead of having this the surgical instruments, instead of having this stainless steel, we can coat the copper on the surface. So for that we use this particular technologies, this is techniques for this coating, and we coated, and we also this again published in a literature. So here what happens, we coated with different layers and we study the antimicrobial properties, and this is very effective. Okay, it's again the material we chosen, and it has to be coated with the copper and titanium, what all the properties. And this I told that the PCM, right, normally the car radiator, if you use the nanofluids. So similarly, we choose this phase change materials for the green building applications. So normally in case of a green building applications, the building will not will have it's energy sustainable. It has to reduce the sustainable material. So for that we have that is we make the phase change materials that uses reduces the energy consumptions. So normally in case of the air conditioning applications, so what will be the comfort temperature that you can feel? What's the comfort temperature? 24, normally 24 to 27 we are comfortable. 24 to 27 you are comfortable, and you are supposed to maintain this relative humidity. So for that, the coil temperature, this coil temperature may be around 14, or the air that is coming out of that particular grill, it may be a 14 degrees centigrade. The grill temperature, if you look at that, it's a 5 degrees centigrade. So what happens here, and again, there's a part load and that is peak load operations. Normally what happens, this is not in case of in India, but in case of abroad and all, if you use the electric power during the peak hours, the consumption may be higher, they will charge heavily. In case of after 12 o'clock, if you use that, the consumption will be, they will charge very less. So what happens, we use the part load operations, and we used to store that energy in a thermal form. And again, this is, I told that this is the comfort cooling applications. So instead of, this is the chiller unit, and this is the storage unit, and here the people are working in an air conditioning environment. So instead of pumping this energy directly into this air conditioning room, we used to have this buffer unit. In the buffer unit, we used to store the cooling energy, and this has to be, whenever there is a requirement, it has to be used in air conditioning applications. And again, this is the PCMs for room heating and cooling. And again, we recently submitted a proposal for the DST. So normally what happens in case of this rural areas, they go for drying applications, right? The food processing and drying applications. In case of this, we go to the rural area, there is again the power, we don't have a continuous power, there may be a power fluctuation. And again, if it purely depends upon the power, what happens? Obviously, the processing cost increased. So what they used to do, they go for a drying. Suppose let us assume that there is a fish product, it has to be dried. So they can use the natural sunlight, right? If you use the natural sunlight, what happens? That particular product will not be in a suitable form to import or to export it. So the food, the quality gets affected. So it has to be it not be in a uniform texture. So what we used to do, we go for a mechanical drying. If you go for a mechanical drying, it has to go with the electrical power. What our intention is, instead of going in electrical power, we used to store the heat energy here, right? So this is a solar collector. This is a solar collector. That solar collector, that heat energy is stored in the PCM balls. that PCM ball will cater the need of this heating applications. And again, during night time also, it can be continuously used without any electric power. And I told that this is a thermal jacket, right? This is a thermal jacket that can be used for adverse climates. And this is the phase change materials. Normally, when it's a liquid form, the thermal conductivity will be very less. If you want to increase the thermal conductivity, we used to add this type of nanomaterial into that. What will be, anybody know the conductivity of the copper? Conductivity of copper? What's the conductivity of liquid materials? Any mechanical engineers? So it may be order of, let us assume that it's an order of 0.5 units. If you take a conductivity of the copper, it's in the order of 400 units. So what we are supposed to do, normally if you keep the water in a refrigerator, how long it will take for you to make ice? Let us assume that I am giving a cup of water. I want to make that as an ice. How long it will take? Hardly 3 or 4 hours, right? If you keep a cup of water in a freezer unit, normally it will take minimum 3 to 4 hours. If you give the same water to me, I will make the water to freeze within 30 or 40 minutes. So why it happening? Because if you go with a conventional water, the conductivity of the water is in the order of 0.5 units. What I used to do, I used to add the copper or any materials into that. I will make, suppose if you are adding copper in water, what happens? If you put a copper rod into the water, what happens? It will disperse, right? It will sink, right? But the intention is we have to make to float. If you make to float, obviously it will have the same properties. Okay, for making this float, what we are supposed to do, we have to make that copper in a nano form. If it make to a nano form, it will have a higher surface energy, and again it will be uniformly dispersed. That's what, if you look at that, the first one is paraffin material with copper oxide. Then the next one is the paraffin with TiO2, paraffin with the combination of copper oxide and TiO2. So here the paraffin with copper oxide, paraffin with TiO2, paraffin, how it has to be, the changes, right? So here again, this is again how long you can add this nanomaterial. You take a water, I told that I can add the copper into that. So how long I can add it? If you keep on adding, what happens at one particular point of time, it will get agglomerated, right? It will, because of higher surface energy, it will get agglomerated. Once it gets agglomerated, what happens? The size becomes nano, becomes micro, and if it becomes micro, what happens? It will settle down. It shows that normally this is the curve. So how long you can add it. So for that, so if you look at that, the 0.8 particle concentration, this weight fraction is the maximum limit. So beyond that, it becomes an adverse effect. So here again, this is again activated carbon. So normally the activated carbon, what we used to do, so now going for a chemical routing, we used to synthesize the same carbon nanotubes with the natural fibers. So here we use the hemp material. Normally in case of a Tamil, we used to say that the pulchakira, right? We use that particular hemp and we dry it and we make this activated carbon. And this activated carbon, this is the PCM, right? This the PCM. The normal PCM, we disperse this activated carbon, and if you disperse this activated carbon, there is the color change. And again, if you look at this property, right, if you look at that, the thermal conductivity enhancement, by adding this thermal conductivity, what will be the enhancement? It will shows that, and this particular phase change material with the activated carbon, we use it for banana storage or banana ripening applications, right? So this applications, it's used. And this is the activated carbon we synthesized in our laboratory. And this is, I told that we invented a material for a comfort cooling applications. So normally what happens, if I make, let us assume that in case of a helmet, so in between, if you place an ice, right, the PCM is nothing but a liquid and solid form, right, then only the energy exchange takes place. If you provide any liquid material above your head, if there is any impact, what happens? If there is any impact, what happens? Obviously, let us assume that I am putting an acid above my head. If there is an impact, what happens? It will spill over my body. It's again create a lot of other problems. So instead of storing that, I can store in a powder form, right? That powder material itself is capable of storing the latent heat. You all know the latent heat? Right, latent heat, right? Normally in case of this ice, if you take an ice, what happens at 0 degree? If you cool the water at 0 degree, what happens? It will retain the 0 degree, right? The water becomes ice. When it becomes complete ice, then only it reduces the subcooling temperature. Maybe it will go up to -5, maybe -5 or -10. Beyond that, it can't go, right? That's latent heat. So whatever the helmet cooling applications, whatever the PCM applications, we used to store as a latent heat. But in case, if it's a liquid, what happens? There's a spillover, there's a possibilities of other cases. So for that, instead of storing this latent, we use the powder material. So if you look at that, this is the next technology, this is the next version of the PCM. If you look at that, the normal PCM, this encapsulation. Suppose I want to capsule the water, I can have a bottle, right? The bottle, any water bottle, can I have this water bottle? Yes, thank you. So normally here, this is a water, right? It's a latent material, latent heat material. I am encapsulated with the plastic. The cylindrical encapsulation. We used to call that as a cylindrical encapsulation. So here, the liquid is stored in this container. If there is any accident happen, what happens? It will spill over. So instead of that, this water itself, I will make that as a powder form. Okay? This water, even at this 24 degree or 25 degree centigrade, it's a powder form. Normally this water becomes a solid at 0 degree centigrade, right? So normally what we used to do, this water is encapsulated, this is a macro encapsulation. This polymer material is a macro encapsulated. Instead of going for a macro encapsulation, we go for a micro and nano encapsulation. This water molecule will be encapsulated with some polymeric material. So what happens, you can take this powder and you can put it in a packet. It can go anywhere. The same technology is here. So here, if you look at that, this at -5 degrees centigrade, it's solid. And this micro encapsulated PCM is again a solid form. At 0 degrees centigrade, solid. Here, it's solid. If you look at this, the conventional phase change material, this becomes a liquid, right? If you look at that, this photograph, it becomes, the solid becomes a liquid. But our micro encapsulation is still in the solid form. Even at 25 degrees centigrade, the normal water or normal PCM, it becomes liquid form, but ours, it's in the solid form. This technology we used for helmet cooling application, the technology remains the same. The materials almost remains the same, but the application changes. We use this application for helmet cooling. We use these applications for thermal jackets. We use the same applications for heating and cooling applications, right? I'm just making this application. By making this different applications, I can have different patents. So that is why it is possible for us to go for a more number of patents, right? It's a very simple technique, because if you know how to make this material, it can be projected to any way, right? So these are all, if you look at that, this is a bottle, right? This is a bottle with cylindrical encapsulation. If you look at this is an encapsulation. This is where the encapsulation, inside that we have the liquids. It's in the micro size, right? Even if you crush it, it will not happen. The same thing, we use it for a building cooling application also. So this again carbon nanotubes we synthesized, and this can be used for tomato ripening applications, right? So previously this for banana ripening, only the application differs, and we slightly change the materials. Once you know how to synthesize any of the material, you just simple modification, it can be used for any other applications, and you can also patent it, you can also publish this work. And the previous work, that is with energy and building, we published this previous work in Energy and Building Journal. So here this work was published in Journal of Thermal Analysis and Calorimetry. Only the slight changes in material and the applications, it's possible for us to publish in 2 different journals. Okay? And again, I told that as a mechanical engineer, we also work with the civil people. If you look at this, the conventional building, if you go with a conventional building, what happens? During maybe after 3 or 4 o'clock, the heat is infiltrated into the building, right? If you ask any HVAC engineers, our botheration is only at 4 o'clock or 3 o'clock only. We have a higher heat infiltration. So because of earth radiations, right? So normally in case of a previous traditional building, we don't have that type of heat infiltration. Even you take our Guindy campus building or AC Tech building, the wall size of very larger thickness. So it will not allow the heat to enter into the building. But these days, so because of the cost reductions and because of the space constraint, we reduce the size of the wall thickness. If you reduce the wall thickness, what happens? The heat will be infiltrated into the building. Okay? And again, if you take an energy consumption, we used to say that our air conditioning unit is a higher culprit of consuming a heavy power. The total energy consumption, if you take a building energy consumption alone, it's more than 30 to 40% of the energy will be consumed by our electrical or our air conditioning unit. So if it's a conventional wall, it will allow the heat into this building. So for that, initially we tried the hollow bricks. In the hollow bricks, let us assume that we are pouring water into that, right? PCM. It's a PCM is nothing but a water. It's a liquid or solid. So if you pour water into that, we fill this gap. It's not a water, it's a phase change material. So what happens it will not allow the heat enter into the building. During night time, it will make cool, and during daytime, it will melt. So the heat will not be entered into this problem. But here what problem is, if you go with this liquid phase change material, if there is any damage happens, if there is any collapse or any incident happen, the entire building get collapsed. If there is any leakage, let us assume that the building you are occupying, there's a leakage, there's a wetness in the surface. Are you comfortable? It's not, you are not feeling good, right? So there's a problem. That is why what we do that, I told that there's a micro encapsulation. It is mixed with this cement, right? Sand, cement, and we mix the powder material into that, and we plaster over the surface. So because of that, it will have the same impact of this. Okay, it's again, we patented this. We are in the process of obtaining a patent grant for this. Okay. So these are all some of the research or some of the project we completed for Department of Science and Technology, and this is for under Young Scientist Scheme. We received the funding. It's around 14.4 lakhs. It was in the year 2010 we received this project. It's again for the nanoparticles disposed with the phase change materials. Okay, these are all the phase change materials we synthesis or we produce, and these are all the nanomaterials we disperse into that. So because of that, we filed a patent. We also received a patent for this particular work. So we have a quantum of PCMs with nanomaterials. So if anybody want to use that, it has to be again a patented technology, right? Yes. And this is the experimental setup we created. So as I told that for drying applications, right? It's again for a funded project. This is for UGC funded project. So here, this is a solar collector. So this is a drying unit. So normally in case of the conventional drying, what the people will do that, they will take the heat, directly go to this drying unit, and it gets dried. And again, during night time, we don't have a sunlight, we don't have a solar radiations, so night time will not be work. And again, if you take any drying products, the performance will be enhanced only if you dry it in a very controlled environment, in a very controlled temperature. You take a fish drying, or you take a banana, or you take a tomato. You can also make this tomato as a dried form. You can also make this dry grapes. You all know that, right? So normally this dry grapes, it's again a dried form. So for that you have to maintain a proper temperature and humidity. So for that we have a solar collector. It will not go directly into this drying unit. Instead of going directly into that, we have this storage tank, right? This is a storage tank. This auxiliary storage tank with the PCM tank. That the PCM tank will store the heat energy, and this can be supplied to this dryer. So because of that, what happens, instead of directly going to that, so it will store in it's like a battery storage. So normally we are storing a battery. A battery can be used for storing the electrical energy. When there is no power, this current can be used. Similarly, this heat energy is stored in an unit, and it can be used whenever there is a requirement. And this is the other project. So this again a DST project. The grant is around 49 lakhs. So this is for defining a thermal property analyzer. As I told that mostly we used to work for the thermal conductivity. So we invented a material. This again, we invented a machinery to measure the thermal conductivity without any distraction from it. The accuracy of that particular instrument is around 99.99. So here, using this setup, you can find thermal conductivity of any solid sample. It's again a patented technology. This is available in our laboratory. It's again a patented technology. And again, I told that this is PCM bricks, right? The bricks that can store the heat and cooling energy. It can be tested in this particular chamber. And in addition to that, we have also the blinds with the phase change materials. So this recent work, this is again a DST funded project. This costing around 37.7 lakhs. This is for the desiccant wheel, right? Normally for desiccant cooling applications, this again a building cooling applications. As I told that building that consumes higher power, and that is with reference to the air conditioning unit. So in case of an air conditioning unit, the latent heat that plays a crucial role. So normally in case of the places like Chennai, if you go to without air conditioning, how do you feel that? You are highly suffocated, right? And because of that moisture that prevails. Normally in case of an air conditioning, if you look at the backside, so water will be dripping, right? That is nothing but the latent heat. In case of an air conditioning, we have to concentrate both latent as well as the sensible heat. So normally the sensible heat, it can be easily reduced, but in case of a latent heat, we require higher energy. So this particular wheel, this again, it's called an enthalpy wheel. It will absorb the moisture, right? It will absorb the moisture. That's a way it can reduce the latent heat. So here again, the same nanomaterials. The material will be the same. The application is slightly modified in a different form. So here we recently filed a patent for this particular work. And this is for electronic cooling applications. So here again, this is a funded project. This is DST. The grant is around 33 lakhs. So here, this is for electronic cooling applications, right? The material will be the same, application only the diverted. So here, this is, if you look at that, that is nothing but a processor of a gaming computer. If you look at the size, it's the size of a gaming computer processor. Above that, we have a heat sink, right? The processor, it's one of the main component that will generate heat, right? If it is not to be maintained to a proper temperature, what happens? The processor performance will be greatly affected. The processor will be effectively work at a temperature of 70 degrees centigrade. We have to maintain the processor below the 70 degrees centigrade. So for that, we have a heat sink. Computer open panni paathirukkinga illaya? So we have a heat sink. Above that, we have a fan. But these days, it's also coming with the heat pipes. In case of in case of a laptop, you don't find the fan sometimes. They have a heat pipes. So here again, we use the phase change materials. The heat sink, it filled with the phase change materials. If you fill with the phase change materials, it will ensure that the proper uniform temperature can be maintained in the processor. Okay? So by using this PCM and heat pipes, you can reduce or eliminate the usage of fan over the above of the heat sink. Okay? That's our work. And these are all some of the innovations we did using this phase change materials. So as I told that the composite materials, right? The composite materials. This is for even it's a natural fiber composite material. If you go with the conventional natural fiber composite, you don't have a strength. So to enhance the strength of this material, we added the nanomaterial into that, and we conducted all these properties. By adding this nanomaterial into that, you can make, suppose, any material, if you want to increase the tensile strength, you have to add the material accordingly. In some applications, you are supposed to have a higher compressive strength. Sometimes you may require a higher ductility. So depending upon the property that you are looking for, you have to add this material, and that will enhance the property, right? Yes. So using these are all the natural fibers, right? We use hemp, loofah, jute, and all this. Even you use the the banana, coir, pineapple oil, these are all the fibers we used for making this natural composites, and these are all the nanomaterials, natural fibers, titanium oxide, carbon, these are all the various nanomaterials we mixed into this fiber materials. So because of that, we have a higher impact strength, we can also have a higher compressive strength, and we too have higher thermal stability. So because of that, it's possible for us to have one Indian patent, and using this work, we also published 3 international journals. So here, it's a very heterogeneous group, that is why I'm giving only an overview, or otherwise I can go deep into that. I can say that what's the mechanism involved in that, and how it has to be improved, and what property, if it's a compressive strength improvement, what are all the properties that you have to make it, and what are all the materials you can make it, that and all we can discuss, because sometimes if I go deep into that, it may be more on the mechanical perspectives. That is why I'm not go deep into that, I'm giving only the overview, right? So this is again, I told that the antimicrobial filters, right? So it's again an antimicrobial filter. That's a filter we invented, and this can be used for air conditioning applications, or in case of a chimney, or in case of the clean room applications also, we can use this particular filters. And again, this is a conventional media filter. This media filters is coated with the activated carbons. And this activated carbon, again, we use to synthesis by using this natural materials. Okay? And we prove that it will have the capability of killing the microbes. So that is why the patent is also granted for this particular work. And if you look at that, the air filtering capacity, right, it reduces the 90 to 97% of the growth of the microbes. So normally, if you go into this air conditioning room, sometimes you may have a fouling smell, right? Then the mechanics, AC mechanics will come and they will clean the filter, right? By cleaning the filter, the smell will be reduced. If there is a fouling smell in the sense, there is because in case of a filter, there is a dust will be accumulated, and in addition to that, if it is near to the chiller unit, if it's near to the chiller unit, what happens? The moisture is also to prevails in that. The moisture and dust microbes, it will make the microbes to grow, right? So this particular filter will reduce the growth of the microbes. It will kill the microbes, and this particular filter will have the self-cleaning capacity, right? The dust will not be accumulated into that. It will be settled down. So these are all, here again using this, we have one granted patent, and we also published 2 international papers in this particular work, and these are all the filters. This all filter material we use, the aluminum alloy, aluminum and polymer materials, and filter materials, filter element is made with the activated carbon from biosources. We also use the natural and synthetic polymers. This anti-microbial materials, we use silver material, silver oxide, we use copper oxide, we also use the gold nanomaterials, iron, zinc oxide, TiO2, Si, SiO2, magnesium and calcium oxide. These are all the various materials, various combinations of material we use for making the filters. So this is a helmet, right? I told that, right? The helmet, the same thing. So this is a helmet. So in between this, the red layer is nothing but a hard layer. It's a hard layer. So this green layer, previously you may find this, the thermocol, right? So the thermocol will be replaced by this, the phase change materials. It will be cover the entire entire skull of your body, at the same time this area also. That is why it's like that. So below that we must have a cushioning layer. Okay, so this green layer is filled with this micro and nano encapsulated PCMs. Okay. And these are all okay. The thermal jacket I told you, right? This thermal jacket, it's a granted pattern again. So here, so this is this again a pouch that is to be placed in the jacket. This is actual thermal jacket. So in this thermal jacket, we used to place this pouch inside it, and this has to be recharged. So normally in case of this adverse climate, so what happens is we have to make this body warm, right? So for that, this particular material can be used. But what happens when it becomes cool, it has to be recharged. For recharging that, we introduce the electrical power connections. It can be attached to a battery, it will re-energized. Okay? And this is the solar cooking. Okay, this this solar collector, the tank, and this is the stove or cooking unit. It can be go to this thermal storage unit. From there, the heat will be going to the cooking unit. And this PCM with the cement material. Okay. So here again, if you look at even I can say so far our group has published more than 100 research articles. If you look at that, we don't do any wonders, right? It's all we are replaced with a material, the same material, right? If you go deep into that, the material synthesis or material productions, it's the same procedure, only a slight modifications, right? If you work on the mechanical background with the air conditioning or refrigeration units, you don't find this type of wide usage, okay? And again, if you go with a conventional way of doing research, you have to know how your research can be converted into an application perspectives, right? Because I have an opportunity to work with, with a mechanical background, in the year 2009, I went to the nanoscience and technology as an assistant professor. There I worked for a period of 3 years. Then again returned back to mechanical. Again I have to transfer to AC Tech campus. I have an opportunity to work with the chemical engineering people. As a mechanical engineering, working with this chemical and other science people, we can get a lot of informations. So these science people or the science background people, they know how to make materials. As an engineer, we know how to use it. So what I did, I get some information from the science people, I applied in the industry. If you take our research, with a mechanical engineer, we have a paper in textile, we have a paper in electrical oriented papers. We also work for biotechnology oriented work. The same material, but the application slightly diversified. And again, in case of a research, right, you must be well organized. If you look at that, there are two type of people, right? So normally, mostly, we will be like this. So whenever there is a problem, I used to say to my research scholar, whenever you have a problem, you must be happy, right? Whenever there's a problem, there's an opportunity to find a solution. If there is no problem, obviously, you don't have a solution, right? Even in case of a mechanical engineering department, getting a single item, it's a very tough. There are a lot of formalities, rules and regulations. Okay, that make me to work very extensively, right? So because of that, we can have more number of papers. And so far, almost 3 crores worth of project we completed. So we must be more organized. And this is the last slide. Normally, this is really required for a researcher. So you have to set a goal, right? So how it has to be? For fixing a goal, it must be a very specific goal. You must be very specific, and it's a measurable one, right? If you say that maybe next day I want to land it in a moon, that is not possible. What possible, that has to be fixed. Very researcher, that is very, very important. So it must be very specific, or otherwise it may be very tough, or maybe whatever they discussed the previous slide, it may not be important. That shows only there are even a single material, how yourself you can make work on this material. As far as the research is concerned, this is very important. You are very specific in fixing your goal, and this goal must be, it's a measurable one, right? Okay. Then it must be an attainable one. If you choose next day I want to be a vice chancellor, it is not possible, right? If you want to be a vice chancellor, at least you must have 20 or 25 years of experience in teaching. Even let us assume that as a researcher you would have you have a thought, I want to work in Stanford University or something else. It's possible, but the next day it is not possible, right? So if you want to work with Stanford, or if you want to work with any other California or any other university, you must have a number of papers. So initially you try for at least 1 or 2 papers. If you know how to write a papers, the first paper, writing the first paper for me took nearly 2 to 3 years. I registered my PhD in the year 2001, and my first paper was in the year 2003. For me, it took, for writing a paper, 2 years. So after that, every year we used to have a habit of publishing more than an average of 5 to 10 papers. Okay? So it must be, initially try to, your goal must be an attainable, and it must be result oriented, right? Or otherwise, it may be very tough. Normally, if you work with a research, sometimes you don't have a result. It must be a result oriented, and the time bound, that is very, very important. Now, because this time, even in case of, that is why I used to say to my research scholar, if you find any new material, or if you find any new innovations, it has to be immediately communicated to a journal, or it has to be filed as a patent, right? If you are not filing it, or if you are not registered as a patent, it will be published by somebody else. And again, most of the time I used to say to my research scholar, for a paper, for writing a paper, how long it will take for you? Let us assume that you all doing your experimentation is over. After completing your experimentation, how long it will take for you to write a paper? On average, any idea? The university requirement is you are supposed to publish 1 or 2 papers, right? 2 papers for a period of maybe 3 years. Full-time scholars, it may be 2 years. So normally, the conducting an experiment, it may take 6 months or sometimes 1 year or 1.5 years. For writing papers, you have to take not more than 15 days. If you write a paper, right, you have to sit continuously without any disturbance or without any hindrance. If you sit, if you write paper continuously for a period of, continuously, if you spend 15 days, that will be more than sufficient. If you write the same paper for 1 month, the clarity will be reduced. If it took 3 months, definitely the clarity will be reduced. If it took 6 months for writing article, obviously there is no stuff involved in that. Okay? So you have to fix a time and you have to work. It's easy for you to excel in research as well as your career. Thank you. This is our research group. Thank you. So do you have any doubt? You can feel free, right? Because as I told that, if it's a mechanical, I can go deep into that. Or I can give an overview, whatever you ask, right?
Good afternoon, sir.
Yes, good afternoon.
Actually, one term I didn't get, sir. You told patent grant. What does that grant mean, sir?
Granted, right? So normally what happens, if you find any innovations, first you have to file it. For filing a patent, it don't require any complications. You may require a quantum of results. Let us assume that I'm inventing this bottle, right? The shape you can change it, material you can change it, it can be filed it. After filing a patent, it will take a minimum of 1 or 2 years. It will be published in a patent journal. Okay, anybody can access it. Suppose the same way, let us assume that this particular girl granted a patent the same way, the same fluid, she will give an objection. So this is my product, you can't patent this. So it will take 6 months or 1 year period. So after that, you will get a notice, you will get some objections. The controller or the previous examiner, right? The patent officer, right? He is one of the patent officer. He will write an objection. He will like your paper, he will give some comments. So these are all the objections. He may give by quoting the several patents. So similarly, there are similar patents are available, right? By quoting the similar patents, he will give an objections. So you have to clarify the objection. You have to write a written statement to this patent office. So these are all the objections you raised for this particular patent. So this is the objection overview, or this is the clarification for this objection. Then after that, they will fix a hearing date. Like in case of a court case, right? How you are appear before the judge. Similarly, we have to appear before the patent officer or controller. They used to call that as a controller, right? So you have to appear before the controller. Previously, it's on offline mode. Now, it's a very comfortable. You can go with online mode. So you have to appear before the controller, and he will raise the objections. Again, he will raise the other objections also. You have to convince and you have to make that your product will be different from other products. Main intention is you have to make the controller, this is unique product. This is different from other products. If he get convinced, then you will get a certificate. Whatever I am projected a certificate, right? He will give the certificate. That certificate is a very valid document. You can have this certificate. That certificate alone will be sufficient for completing a PhD. You have one granted patent, that is more than sufficient for completing a PhD. That's one part. Other part, let us assume that somebody is making this water. You can file a case. They are supposed to pay, right, money for you, right? For using this, they are supposed to pay some amount for you. That's a way, if you work with bio-related activities, so here there are a lot of duplications happen, but in case of bio-related aspects, it's easy, you can also generate revenue from this. That is why in case of a US, you can take any US patent. Mostly they don't work. They work only a limited period, they will try to file a patent. Our problem is, we have to, how to differentiate from US patent. What they used to do, I projected a lot of phase change materials, right? How they file it, and the US people, very particularly the US people, organic, inorganic materials or PCMs. In any material, right, you take, it's coming under organic and inorganic PCMs. And you have to justify that they are quoting in a very broad manner. I'm telling this organic material. All materials coming under organic or inorganic materials, right? They are very broad, that's the way they used to generate money. Okay? So, maybe initial period, even your idea can also to be patented. I have an idea like this, it can be patented. Right? Or otherwise,
Even for idea they give grants, sir?
Yes?
Even for that idea they give grant?
Idea in the sense, how to make this. You must have a rough idea of that. Idea in the sense, how to make this.
No, what I mean to say is, I am an electrical engineer. I have a design for some converter or something.
Okay.
I have an idea. I have not simulated. I have not.
That can be
modeled it.
registered.
Outcomes have not been recorded.
That can be registered. That ideas can be registered. They will have a 1 year time, right? So before that, you can try to collect the results and try to project it. At the time of objection, you can show these results. That will be more than sufficient. Even for my students, whenever they are registered, with the first 6 months, I ask them to file a patent. Even the previous paper, the first one, right? The last slide, I told that enthalpy wheel. Before publishing the article, that is very important, right? So before publishing the content in a research article, it has to be patented. Now, because if you publish it, it's open, right? You can't say that is my technique. So first you file a patent. Let us assume that I am filing a patent today. Tomorrow you can publish it.
Okay.
They will refer only the yesterday content. So first step is, before publishing a paper, if you file a patent, it may require, they are charging only 2,000 rupees. Even anything you can patent, right? At least you have a hands-on experience. Once you appear before this hearing, you will get a lot of idea, right?
Okay, sir. One thing, sir, so many applications you have identified, not tried of any startups, sir, with this?
Sorry?
Not tried of any startup with these applications, sir? Startup.
Startups. So here the problem is,
Since see the application,
Yeah,
I
yeah,
was
it's
very
good,
much
it's
interested.
good, it's
Thought that
good.
it is a commercial value.
even we initially discussed with Lucas TVS and other industries. Now because I am working as a regular professor here, right? I can do some consultancy alone. Still, there is a discussion going on in a higher level. Even the last syndicate or before the last syndicate, from the Center for Entrepreneurship Development, Dr. Saravanan, he was the director of that particular center. He projected why the faculties can, why not the faculty can start will have startups. But the government, central government, they have an objection, right? If I have a startup, I can I generate money, right? So the state government will not have.
Conflict of interest.
Yeah, they are not giving a signal, or otherwise you can start startups. But what we used to do, we will make this as a consultancy work.
Okay.
We also did a consultancy for Lucas TVS, that is for the electroplating, right? So normally for the electroplating applications, the entire cabin, entire chamber has to be maintained at a uniform temperature. Then only the plating will takes place at a proper temperature. So we do consultancy and we generate money. And we also did a work for the PCM for start-stop for Lucas TVS. One for Brakes India, the other for Lucas TVS. That way we generate money. Startups, we have a constraint. The government is not giving a signal to
One
us.
small thing, sir. I thought of avoiding it, but still, this PCM, does they have it's a technical thing, they have a lifespan or it's an infinite lifespan?
It will have a lifespan. It will have a lifespan. It will go up to for 10 to 20 years.
That much? Okay, fine.
Yeah.
Sir, good evening, sir.
Good evening.
How ceramic materials find its application in wastewater treatment? And second question is, what about the wastes generated from these nano materials? And third thing is that you are mixing lot of nano materials. how to arrive at the final composition, whether based on material properties or...
It again depends upon the application what you are looking for. So I told that the same material I used for banana ripening applications. The same material but different combination I used for tomato storage applications. Right? The temperature changes. So depending upon the requirements, you have to tailor-made your nanomaterials. That is why I told that initially we started with top-down approach. If you go for a top-down approach, you don't have a tailor-made applications. If you go for a bottom-up approach, you can tailor-made. Sometimes in some applications, you may require a higher thermal conductivity. In some applications, you may have insulating properties. Even let us assume in case of a gas turbine, right? It's a very large turbine. If we increase the combustion temperature, the pollution that is coming out will be reduced. If we increase the temperature, what happens? The material will not withstand. So what we used to do in the turbine, the entire turbine material is made with that type of hard material. Is not possible. We go for a coating over that. Okay? So it's again application perspectives. And again you told that the toxicology, right? That is why I told that initially we tried with chemical material. Now we move on to bio-based, natural materials. Anyway, it's a waste. So I told that this is the filter is made with the activated carbon. That activated carbon is synthesis from hemp. That's a natural source. Right? So if you go for a natural source, it's a waste. Instead of wasting that, we use it for. And again, I told that this is a natural fiber composites. Previously, they go with metal matrix composites. Now, we are going with the material that is available from the nature. Okay?
Thank you, sir.
Thank you, sir.
Thank you, ma'am.
It was indeed a pleasure listening to your research on materials and the possibilities of conducting several research studies using the same material by varying the applications. And I think this session was timed appropriately after the patent session so that you can actually see the patent certificates that sir has got, and you can also try these things in your own research experiences coming in the days. We thank you, sir. We thank you for your time and expertise that you have shared with us. I think the second day of the session is now over, and I thank all the participants also for participating and interacting with the resource person. Thanks a lot, sir.
Thank you. Thank you. Before completing my talk, as Madam stated that we have quite a number of patents, right? Normally, the first patent that is I filed in the year 2009, that's again with the phase change material. For getting the granted, it took more than maybe 2018 only, I received a certificate from the patent authority. So after obtaining this granted patent, then only I will come to know that publishing paper is a tough task, writing patent is a very simple. So after that, I continuously, maybe if you look at my resume, after 2018 only, we filed around 11 patents. Even in our laboratory, recently we have a student join in our research group. I asked her to file a patent. So whenever the student joined, immediately, maybe within 6 months before completing their coursework, I make to file a patent. It's easy for publishing a paper. At the same time, the credential is also to be in place. Thank you.
Excellent. That's excellent. So because you must be knowing, as per the PhD regulations, patent is also accepted instead of publication. Okay, a granted patent. So if you go through the regulations thoroughly, you will understand. And tomorrow we have a session on PhD regulations. Kumaresan sir will be talking in detail about this particular regulations. So thank you. A round of applause for our resource person.
Thank you. Thank you, ma'am.